That nature has spent 500,000 years in research and development on this subject. And so I think it is something that we can certainly take advantage of and that we can learn from ourselves. Somebody asked me a question about how does it impact the biology of the soil if we come in and because I mentioned that the slicing and dicing and plowing and grading and so forth is really pretty destructive. And so they were asking about that, because they rototill their garden. And should they be rototilling their garden? And my answer to that is no. You really shouldn't do that. Maybe you can do it at the very beginning. Maybe the garden is like this. It's arroyos and hills and all that, and you got to start with something. You can't manage it very well when it's all over the place. So you have to get it to a grade that is manageable. But once you have it to a grade that is manageable, don't till it anymore. When we try to garden, when we try to manage a landscape, we're battling this evaporative loss of moisture constantly. We can lose, and on some days, a whole inch of water can be lost off of a pan of water. On a really hot, dry day, a whole inch can disappear. Okay, well, soils can get hot too, and psss, all the way the moisture goes. Solution? In addition to holding moisture in the soil using humus, the other part of the equation is put a protective scab over that surface of mulch, organic mulches, which will hide the soil from that hot, dry environment. And that'll help preserve moisture. And in time, the saprophytic bacteria and saprophytic fungi will come to the surface and say, oh, yeah, food stuff. And they'll start to eat that mulch and break it down and introduce those mineral cations and anions back into the soil. So your mulch will go away. You have to always be on guard and add a little bit more. Because once you get that microbiology doing what it's supposed to do, you want to leave them alone. You want them to perpetuate themselves. And so instead of having to do that, manage that site, combat your weeds by mulching them out, by not letting them grow there in the first place. Put mulch down. And then when you're ready to plant your tomatoes or your chilies or whatever it is you're going to plant, and you come along and scrape the mulch aside, open up a little hole, plug in your starter plant, tuck it back in, pull the mulch back or whatever, and off you go. If you look in a compost pile or in a soil and you see this stringy looking mycelium hyphae looking stuff, that's not the mycorrhiza. You can't see the mycorrhizae. They're too tiny. In fact, I want to pass around. This is a sample of soil taken from my arboreta. When we started this process, this was collapsed clay. We talked about why clay will collapse. And so if I were to dig a hole, if I dug a hole the size of this pail and added water to it, that water would sit in that hole for over a week. It wouldn't drain out of there until it evaporated out. It wouldn't soak out, it would evaporate out. Well, today, if I dig a hole that size and fill it full of water, it'd probably be gone in an hour or two. It would soak in because the soil has become so porous. And if you look at the particles here, they are now in aggregates. And even if you water this spot, the aggregates will hold together because they are choked full of mucus and proteins and humus that are pulling the particles all together into those little conglomerates. And that's what happens to the clay. That's why this whole process works. So I'll pass this around. Don't eat this. But it's just neat. You look at that and go, that's clay? But it is. And if you were to dissect one of those and open it up, you would find in there those hyphae of mycorrhizae have gotten in there holding it together. Glomalin, apparently I forgot to put it in this particular presentation, but glomalin is one of the reasons why these aggregates are also holding together, because one of the byproducts of mycorrhizal function in the soil is a protein glue called glomalin. It is a word that was derived from the mycorrhizae that made it. The mycorrhizae is called glomus. Now there's many species of glomus, and this category of mycorrhizae will work with the vast majority of plants that you will ever use in your garden. Corn, strawberries, raspberries, whatever. Most of the plants you will ever grow will associate with one of the glomus species. They are a worldwide family of mycorrhizae. They can be found on the northernmost tundras, north slope of the Alaskan mountain ranges that flow down into the Arctic Ocean. They can be found there. They can be found in the hot Chilean desert. If there's a grass growing out there, there's going to be a glomus on it. So they're very, very, very prolific in all ecosystems of the world, except the yards that we build, the landscapes that we build. So, yeah.
Are these, do any of these mycorrhizal fungi have fruiting bodies? Or
yeah, they do. The glomus does not. Glomus creates a what we call a propagule, which is a seed, a spore, that will be, there's two types. There's one that will be outside the root of its host plant, and there's another one called a vesicle that is inside the root of its host plant. And they're microscopic. They are really, really small. So a grower of mycorrhizae would have to find a way to collect those off of them. The only way you can commercially produce them is to grow plants and inoculate the plant in a commercial growing, like a greenhouse environment. And then when the plant reaches maturity, then you would take the plant and take the root system off of the plant, and then you would grind it up very carefully and then run it through screens and very carefully separate those propagules and vesicles from all of the organic tissues, the root tissues. And you wash them and screen them and wash them and screen them until you're down to just pure spores. That's how it's done commercially. So it's a pretty labor-intensive process. Now there's another type of mycorrhizae called an ectomycorrhizae, and they will, ecto means outside, endo means inside. The ectomycorrhizae will make their fruiting body outside of the plant by producing a puffball or a mushroom or a toadstool or something of that sort. And you probably have seen an ectomycorrhizae by, when you're hiking around in the foothills here, and you're coming across a strange little thing that's kind of like protruding out of the ground, and you go, oh, it's not a mushroom, it's not a toadstool, what the heck is that? It sort of has like a little dome appearance, like pushing the soil up, and then you kick it and it goes poof, and you'll see it like billions of spores floating all over the place. That's an ectomycorrhizal fruiting body. And again, the commercial producers have to be able to grow a plant that will associate with the exact species. Truffle that is found on the roots of oaks in France. That is a mycorrhizae. There's black truffles and there's white truffles. But the truffle, being a mycorrhizae that will associate with that particular type of oak, which is Quercus robur, the common oak of Europe, some people call it the English oak, it will beneficially infect the root system of an oak and do everything I talked about. Find water, find nutrition, give it to the oak. But then it'll make this underground fruiting body that we can actually eat, and very, very valuable commodity. So, so far nobody has figured out how to transfer that technology to North America and commercially grow oak trees with truffles attached to them so that we can get rich. Because truffles are very, very, very expensive. I think a 2-pound truffle is worth $200,000. So anyway, but again, if you let that truffle dry up, finish its maturation process and get dry, and you then dug it up and very carefully opened it up and captured all of the spores, then you could use those spores to infect oak trees and start your own truffle plantation. I just don't know anybody who's really successfully done that. They haven't quite figured out how to make it really work.